Okay, good morning.
Morning.
Okay, let's get started. Today we're going to look at section 11.8. We'll look at these things called power series. That's a nice name, power series. Yep. So what is a power series? We've seen this before already in some context. It's a type of infinite series, of course. And it usually looks something like this. Some coefficient Cn times x to the n. Now, without the x to the n, we just have regular infinite series. And we know what to deal with that in many, many different ways. But now we're going to tag on this x to the n here. So what do these look like? They look like this. You start at 0. So the first one is just a constant c sub 0. And x to the 0, of course, is 1. So there's no x in the first term. But then next one, when n is equal to 1, we have c1 x to the first, and then c2 x squared. And this keeps going. Okay, so we got this series here that has a bunch of coefficients and also a bunch of x's. Now, anytime you write out a series, you have to make sure that this thing converges. If a series doesn't converge, then there's no point in dealing with that in any way. And of course, now with these x's in here, we expect that x will affect the convergence. All right, so x is going to affect the convergence, of course. Let me give you a very, very simple example where you can see that x is going to be the thing that dominates the convergence of the series. Let's make all of these constants 1. And then we end up getting just the sum from 0 to infinity, x to the n. So all of these c's are 1 now. So we get 1 plus x squared plus x cubed plus x to the 4th plus dot, dot, dot. All right? And what does that look like? We've seen this before. Geometric series, very good. Right? Remember, we have 1 plus r squared plus r cubed plus dot, dot, dot. Right? This is a geometric series. So, can you tell me what does x have to be for this power series to converge? Right, very good. Converges if the absolute value of x is strictly less than 1. Okay, so that's the idea behind a power series. We're going to compare to something that we've seen before, and we're going to apply a test to find out when this thing converges. Now, the only extra wrinkle here is we have to find out, because of all these x's in here, we need to know when this thing is going to converge and for what values of x. More generally, a power series can include one more parameter in there. So instead of just x to the n, we're going to have x minus a, the quantity to the n. Once again, all this is just, you keep counting these things starting with n equal to 0. And really, this is just a translation, a horizontal translation. The a changes where you start now. So what this a is called a center. So if I draw a line representing all the real numbers for x to the a would be somewhere here. And what happens is that this series is going to converge in some neighborhood. Can't spell that word, so let's change the word. In some region near x equal to a, or centered at a. And it's going to be symmetric. So this a determines how far you can move from a for that series to converge. And for the one we look at when we started today's lesson, without the a here, you're going to interpret that this as a equal to 0. So the center would be at 0. And once again, you can hover near that 0 up to a certain distance for the series to converge. All right? Looking at this interval here, yeah, question?
When you have an a greater than 0, does the absolute value of x need to be less than 1 for the series to converge?
That may change this thing a little bit. The width is not going to change, but where you start, where the center is going to change. So when you write out the interval, it's going to be affected by a. And we'll see examples today where a comes in and how that changes the interval. Good question. Okay? So this interval here, half of it is called the radius of convergence. And usually we use capital R for that. So here's another R here. And as you can see, when you talk about convergence of a power series, this R is one of the key numbers that we have to figure out. And also one more thing, at the end point here, depending on what the series looks like, the endpoints themselves may or may not converge. So sometimes we might need to use a square bracket for that. But it's different for every series. And that's also something that we have to figure out for each series. Everything in between is pretty clear-cut. They're all going to converge, but anything outside is going to diverge. But on the boundary, maybe, maybe not. All right, so examples of these power series. For what values of x does make that a 1? Okay, as a reminder, remember the starting n doesn't change the convergence. I had to make this a 1, otherwise I would start with a 0 in the denominator, and that's, of course, trouble. So I'm going to start with a 1 here. But that 1 has nothing to do with the convergence. It'll change the sum if we're looking for the sum, but it doesn't change whether the series converge or not. Okay, so the basic idea here, as you saw earlier, is to treat it like a geometric series and then apply some kind of test to determine the convergence. And all the tests that you have learned are available to use, but the most convenient test to use is the ratio test. You should be able to use ratio test to take care of all of these power series that you will see. Okay, remember, here's the old form of the ratio test. But here, things change a little bit, just a little bit. Because each of these an, in this context here, is the coefficient times x to the n. So an becomes cn x to the n. That's the generic term in our power series. The next term down the road is, of course, all of these things with n changed to n plus 1. Basically, you just take that, change n to n plus 1, divided by the old thing, and then you figure out the convergence by making sure this is less than 1. Okay, so let's go ahead and do that. Change all of these n's to n plus 1. Divide by the original term. So just like before, we're going to multiply by the reciprocal because we have a complex fraction here. Right, so there's my n plus 1 term, and here's my nth term. And just like before, you group things that look alike and then simplify. I have a minus 1 to the n plus 1. I'll write it like that. And then downstairs, I have minus 1 to the n. Then I have cube root of n over cube root of n plus 1. That's equivalent to cube root of the whole thing, n over n plus 1. And then finally, x to the n plus 1 over x to the n. I'll do the same thing I did with minus 1. Okay? And there should be a bunch of things you could cancel. Minus 1 to the n, that goes away with that. X to the n, x to the n. And what does this do? When n goes to infinity, this becomes 1, right? Because the stuff under the cube root is about 1, so therefore this is 1. Okay. Now what we got left here, when n, after n went to infinity, we have the absolute value of minus 1 times x and of course the absolute value of minus 1 times x is the same as absolute value of x because of the power of absolute value. All right? And how do we make sure this converges? Strictly less than 1. Good. So now that's telling us that x is between minus 1 and 1. Now the tricky thing here is, remember, when x is exactly equal to minus 1, then the ratio is exactly equal to 1. That's when the ratio test doesn't tell you anything about the series. So we have to check the endpoints, because the ratio test would not tell us about what happens at the endpoints. That's one of the weaknesses of the ratio test. So we got to check that. We answered most of the question here already. We're saying that we guarantee the series to converge strictly between minus 1 and 1. But it may still converge on the endpoints. So now we check. And let me rewrite the series. Well, not rewrite, but bring it back. So this is a series that we are looking at. We already know it's going to converge between minus 1 and 1. Now we check the boundaries. And what you do is you take this value, put that into your series, and see what it looks like. If I put in minus 1 in here for x, then I get minus 1 to the n, the original one, and the new minus 1 to the n, all over the cube root of n. And now if you multiply under the n power here, you get 1 to the n, right? But that's just 1 over the cube root of n. These minus 1s multiplied together gives you a 1, and 1 to the n doesn't change anything. Okay, now we look at this series here. We have to ask ourselves, does that converge? So let me ask you that question. Does this series converge, and why? No, good. And why not? Excellent. So this thing diverges because it's a p series with p less than 1, right? So it does not converge. Next, we do the same thing at 1. When I plug 1 in here for x, we have 1 to the n just like before, but this time we have an alternating 1, minus 1 from earlier. So we get this. And does that converge, and why? It's an alternating series, so think about the criteria in alternating series has to meet for that to converge. It does. What are the two criteria then? It goes to 0 and decreasing, right? And which, if you look at this thing here, 1 over n cubed, that satisfies both criteria. So this will converge. Converges because it passes the alternating series test. Okay, now we can modify the interval in which this series will converge. So earlier we said we guarantee minus 1 to 1 strictly between. And now we're going to add one endpoint on the right because we found that it does converge, but the left endpoint diverges. So we say that the interval of convergence is minus 1 inclusive to 1 not included. The other way around. Oh, that's right. Oh, what am I doing? Minus 1, don't want it. 1, want it. Good. Thanks. All right, so this thing is centered at 0. We can go all the way to minus 1, just not touching that. We can go to 1, and we can include it. So everything in between here are the x values you can have for that series to converge. But everything outside as soon as you step beyond 1, that series is going to diverge. And as soon as you touch minus 1, that series is going to diverge. But anything in between is okay. So what's the radius of convergence then? From center to one of the boundary is 1, right? So I can start from here. I can move to the right by 1 or move to the left by 1. So that's the radius of convergence. So that's 1. All right, so now this series is going to converge for infinitely many value of x as long as it is trapped right between minus 1 and 1 and including 1. Okay, questions on this? Good? Good. Let's do a few more. Try this one. N is 2 to infinity, x to the n plus 2 over three times n factorial. All right, so another power series. We start at 2. Again, that 2 is irrelevant. Doesn't matter where we start. The thing is going to converge regardless of where we start, or diverge regardless of where we start. You can't change where you start to change the convergence. Just like last time, we will apply the ratio test. So first we change all the n's to n plus 1. That n turns into n plus 1, and then the original plus 2. And then downstairs is 3 times n plus 1 factorial, right? So that takes care of the n plus 1th term in the series. Now we divide by the nth term, or multiply by the reciprocal of the nth term. And then just like last time, you group things that look alike, simplify, and then come to the conclusion. Let's group the factorial stuff together. First of all, let's just kill off the 3 now. Doesn't do anything, so go away. And then downstairs we have n plus 1, right? Remember, we've done this before. We'll rewrite that as n plus 1 times n factorial. And then upstairs is n factorial. And then x to the n plus 3 over x to the n plus 2. That leaves just one factor of x. We have one more x up here than down here. The rest of them cancel out. And now the n factorials go away. All right, now we let n go to infinity. And what does this do then? Goes to 0, right? So what does that mean? Does it converge? It converges by the ratio test, right? So it's less than 1, so converges. But the question is for what values of x? What do you think? Let's just choose a few values of x. If I put in x is equal to 1, is that thing going to converge? If I put in x is equal to pi, is that going to converge? If I put in 17,982, is that going to converge? Yes. So what is the answer to that question? All real numbers. Good. Excellent. So converges for minus infinity to positive infinity, or What is the radius of convergence then? Yeah, infinity, right? We start at 0. I can go as far right to infinity and as far left to negative infinity. So it's infinity. Okay? Later on, we're going to encounter a bunch of series that look like this with infinitely large interval of convergence. Those series are usually very, very nice for applications because you know whatever value of x you can put in there, that series is going to be meaningful. You occasionally run into series that will diverge for all values of x except one number. We'll see that not today, but maybe the next time we look at power series. Okay, question on that last example? All right, so now let's answer the question, what happens when A is in there, right? Remember, we're dealing with these power series, and so far we look at what happened when we center at A equal to 0. What happens when A is not equal to 0? Here we have minus 1 to the n, x minus 7 to the n over 5n plus 1. Now this time the center is 7. Nothing changes as far as what you do. You just go ahead and apply the ratio test. So we get the n plus 1 term. And then downstairs, change that n to n plus 1. And the original plus 1. Then we divide it by the nth term, or multiply by the reciprocal of the nth term. Then, as usual, you group things that look alike. The minus 1s. The 5n and stuff. Downstairs, we get 5n plus 6, right? And then the x to the x minus 7. Then you start taking things out. We have one more factor of minus 1 upstairs than downstairs, so one of them remains. Here, well, that's going to go to 1, right? So we'll leave that alone. And this guy turns into x minus 7, just 1 power of that. So, finally, when n goes to infinity, the middle one goes to 1. So we have minus 1 times x minus 7. But that minus 1 is irrelevant because we're taking the absolute value. So that's just absolute value of x minus 7. As usual, we require that to be strictly less than 1 in the first step, because that's the only thing the ratio test can be conclusive about, when the ratio is strictly less than 1. Okay, so this is saying that x minus 7 is between minus 1 and positive 1. Therefore, if I add 7 all the way through, now we guarantee everything between 6 and 8 is going to make the series converge. Okay, so that's the initial interval here. But remember, we still have to check the endpoints. Those are places where the ratio is exactly equal to 1 when the ratio test was inconclusive. Now we check x is equal to 6. You take the 6, plug that in for your series. We get minus 1 to the n. 6 minus 7 is minus 1. So another minus 1 to the n over 5n plus 1. We've seen this before. The two minus 1 to the n's together will just turn into a 1. So this is going to be 1 over 5n plus 1. Does it converge? And why? What does it look like? It looks like 1 over n. It's the harmonic series, right? So therefore, it's going to behave like it. So one thing you could do here is to use the limit comparison. Compared to 1 over n. And you'll come to the conclusion that this will behave just like it, and therefore it will diverge. So this will diverge. Okay, now we check 8, right? We check 8. When x is 8, then we have 1 to the n up here, and that's just 1. And downstairs is 5n plus 1. Same question now, does it converge? Yep, another alternating series. The two things that it has to pass goes to 0 and decreasing, and both are satisfied. So this will converge by the alternating series test. And now we know more about the endpoints. We modify the interval. By the way, does the result of these two things change the radius of convergence? No. So you could have answered the radius question right here, right? Because that's not affected by these two. But then these two will affect the interval. Now the interval of convergence is, we don't like 6, but we like 8. So 6 to 8 with a bracket there. Radius is what? What's the radius? 1. You take, right, you center at 7, and you go 1 and 1, so that's your 1. So again, this is not affected by convergence at endpoints. In other words, if the question simply asks you to find the radius of convergence, then you wouldn't need to check the endpoints. If no one asks you what the interval is, but simply the radius, then the radius is very easy to answer. The endpoints just add a little bit more to what you have to do. Okay, let's do one more. All right, so we have x minus 14 to the n over n to the n. Once again, we'll apply the ratio test. Downstairs, this gets a little strange. It's n plus 1 to the power of n plus 1, right? And then we divide by that, so multiplying by the reciprocal of that. Then we group things together and do some stuff and answer the question. So this requires a little bit more analyzing. We'll come back to it. The other part is easy. It's just x minus 14. All right, now, I want you to take 1 minute and think about what to do with this here. Now, be very careful. Whenever you have n plus 1 in the exponent, we can't just say that n and n plus 1 are roughly the same. When you raise something to something slightly bigger, it can be a much, much bigger number. So think about what to do with this thing. Take your 1 minute. All right, that's about 1 minute. So what do you think? What do we do with it? It's going to 0, yeah. Can we actually prove that by manipulating that expression? The conclusion is right. Very good. What do you think? Yeah, excellent. So here's what he's saying. Both answers are right. Because one thing you could do is to reason that whatever this is, because this exponent is always bigger than that, this will always be bigger than what's above. So therefore, eventually shrinks to 0. To be more sure about it, here's what we can do to prove that's the case. This n plus 1 here, you could rewrite the entire thing downstairs as n plus 1 to the n times additional 1 factor of that. Now here, because n plus 1 is not in the exponent, we have about the same number raised to the same power. This will eventually go to 1. And this will eventually go to what? 0, right? 1 over n plus 1 when n becomes large. So this entire ratio eventually goes to 0. Zero is great. We've seen that before because that means the interval is, what's the interval? Yeah, minus infinity to infinity. And the radius, of course, is infinity. So that's another well-behaving series. Whatever you're going to do with it, you can be very certain that whatever x you toss in there, this is going to be a convergent series, and therefore, it's going to make sense. Questions? Okay, great. Well, that's it for today. See you Wednesday. Okay, here.
Can I just check, use the PowerPoint?